Spina set. Hello. Just about ready to get started here. Test, test. Test, test. That's working. Let's check the bench camera. It's working. Let's check the bench camera. Testing 1, 2. Yeah, excellent. And the capture card's functioning. Haha. Excellent. I can hear stuff. You can hear stuff. I can see stuff. You can hear stuff. I can see stuff. Not too shabby. Excellent. Huzzah! Hello! Hello, everybody. How are we doing in this fine landscape of stuff and things known as the internet? I myself have a big old cup of coffee, which is excellent because I could use the caffeine. Come on, Tracking. Come on! Come back! There we go. Much excellence. Ah, glorious. Alrighty. It has been a while. I hope you all are doing well. I wanted to do some more 30 Days Lost in Space because honestly, I missed it. I don't know if you have, but I had. So tonight, we're gonna have a little more fun with computer bits and bobs. We are picking up with day 8. I chuckled at myself because I had to look at the previous VOD. I'm like, what day did we leave off on? I actually forgot to mark day 7 is completed. It felt a little bit like a goober. Naturally though. I do actually have everything still hooked up from last time. But I believe we're done with that for the time being. So we are going to jump into it. All right, so I got this. Let's see, day 8 is adding some color to this dark place. Her. I'll take it. And I'll pause that. And let's see here. I need us to not double up on audio. So I gotta toggle that one. Yeah. Wait, am I silly? No, because that's its own device. Okay, fantastic. All right, yes. All right, let's see what we're doing here.
Rise and shine, Explorer.
Hello.
Day 8 has dawned upon us and has left us with no time to waste. Today, we're stepping up our game. We're going to add a dash of color to your monotonous existence by using a nifty piece of hardware called an RGB LED. Allow me to explain. RGB LED stands for red, green, blue, light-emitting diode. What this LED does is allow us to produce virtually any color on the spectrum by controlling the intensity of the 3 colored diodes. It's like your own personal rainbow producer.
Nice.
We're also going to cover a new function today, analog write. It allows us to send an analog output signal on a digital pin. Yes, I know what you're thinking. Didn't we just discuss how digital and analog are separate entities? We sure did. Let me, however, introduce you to the world of pulse width modulation, or PWM.
Oh, no.
This savvy little trick allows us to fake an analog output on a digital pin. Pretty neat, wouldn't you agree? Nonetheless, that's enough jabber for now. Rest assured, all this and more will be covered as the day progresses. Brace yourself in, Explorer. We've got colors to mix and a spaceship to fix. An RGB LED is unlike your usual kind of LED, Explorer. It's like a 3-in-1 special. Inside that tiny package, you'll find 3 separate LEDs, one red, one green, and one blue, as these are the primary colors of light. In a regular LED, you apply power and it emits a pre-programmed specific color. In an RGB LED, however, you have the ability to control each of the 3 colors individually. You can turn on the red LED, the green LED, the blue LED, or any combination of the 3. So, why is this exciting? Because by varying the intensity of each of these colors, you have the power to create virtually any color you want right at your fingertips. How deeply thrilling. Need a soothing aquamarine glow to relax? Easy. Want to flash a warning in bright alarming red? Ask and you shall receive. In essence, with an RGB LED, you're not just getting one color. You're getting the whole spectrum. Enjoy the possibilities, Explorer. Okay, Explorer, let's dig into 2 intertwined concepts, analog write and pulse width modulation, or PWM, which are critical for controlling our RGB LED. Analog write is a function in Arduino that helps us generate PWM signals.
Okay.
Despite its name, oddly enough, analog write doesn't really deal with analog signals. It's a bit of a misnomer, which could be a source of confusion. Have no fear, Explorer. It'll all piece together soon enough. Moving on to PWM, pulse width modulation is a technique used to create a kind of fake analog effect using digital means. By rapidly switching a signal or power source on and off and changing the proportion of the time it is on versus the time it is off, we can vary the intensity of power that is received. This is important for our RGB LED because it allows us to control the intensity of each of the red, green, and blue LEDs, which in turn lets us mix our colors. Imagine PWM as a fast flickering light. If it flickers so fast that your eyes can't catch it turning on and off, the light will appear dimmer or brighter based on the ratio of on time versus off time. If it's on more than it's off, it appears brighter. If it's off more than it's on, it appears dimmer. In terms of our RGB LED, we'll use analog write to send PWM signals to each of the red, blue, and green LEDs. By changing the duty cycle of the PWM signal, that's the on time, we can control the brightness of each LED. By mixing different levels of brightness across the red, green, and blue LEDs, we'll create the color we want. You're in for quite a treat, Explorer. The trajectory of your future will soon become a lot brighter, quite literally. It appears we've Talk the talk, now let's walk the walk, explorer. Our task today is to light up our RGB LED and give it a whirl. Remember, with pulse width modulation, we can tinker with the intensity of each color, from a meager 0 to a dazzling 255. Talk about a spectrum. Now, one way to control our RGB LED would be to separately define the red, green, and blue values every single time we want to change a color. But frankly, that's like choosing to walk across the galaxy when you have a perfectly good spaceship. It's slow, and it'll leave your code looking like a debris field of supernova. Let's be smarter, shall we? What do you say we build a function to streamline the process? Something catchy and memorable like set RGB red level, green level, blue level. You'll see those 3 byte variables nestled inside the parentheses, separated by commas. These are parameters, and we'll be handing them over to our function like instructions to a well-trained robot butler. We don't have a lot of memory, so since max value doesn't need to be anything higher than 255 anyway, remember, pulse width modulation, a byte is perfect since its max value just so happens to be 255. Using something like an integer
convenient.
for an unsigned number less than or equal to 255 is just a waste of memory. Once we're inside the function, it's time to put those parameters to work. We'll use analog write to set the value for each of our 3 color pins. Efficient and tidy, just the way I like it. In our main loop, it's testing time. We'll call our snazzy new function in a variety of ways to make sure our RGB LED isn't just sitting there like a lump of plastic. Once we're confident everything's shipshape, we'll beam it up to our board and enjoy the show. Let's get to it, Explorer. Lights, camera, code. Now, for what you've been waiting oh so patiently for, let's turn to some instructional material that I was able to gather cached on the computer. I've also added this to your mission resources for future reference. See you soon.
Hello, everybody.
Hee. Alright, so that's our overview. And now we get to poke some stuff and do some things. I'm ready. I'm ready to rock and roll. Let's see what we're dealing with. I'm imagining, I think there's only one of those multicolored LEDs in this kit. And yeah, okay, we're wiring one. All right, I'll take it. All right, so looking at the diagram and the flyout in the video is that the grounding leg I could see here is going to be to our left. And I believe that means that blue was first, so it's blue, ground, and then green or red. I wasn't paying attention too closely to what the other 2 legs were, but that's okay. Looking at this too, so we're sending our signal out on pins 9, 10, and 11, with ground being return, of course, and we have the 1 ground pin. So we're going to get this wired up. And then we're going to take a look at the code down here. Just kind of want to peruse through here. So we've got interesting, okay. I'm not gonna lie, there's definitely a little bit more code to this than I actually was anticipating. It's not bad, it's just more than I anticipated to make it work. Well, I mean, in all fairness, it is also dictated in how we decide to interact with it. So, we're gonna switch to the bench, let's get this wired up, and then go from there. Wow. All right. Take you guys over here with me. So I've got you over here so I can see chat. Much excellence. Okay. All right. So, first things first, I can unplug this stuff. Looks like we need a total of 1, 2, 3, 4 wires, ground being one of them. So I am going to leave ground just plugged in where it is because that's fine. And then we're done with these two from last time. Now last time we were playing with the hi Pyrex! Welcome on in. Hope your day's been treating you well. We were playing with the photo resistor. Took me a second to remember what it was called. Indeed, Pyrex, we're going to be playing with a multicolored LED. I'm really looking forward to this because honestly, I've never programmed one of these before, so it's definitely a little more than I anticipated. But I'm up for the challenge. I think we're gonna have a little fun here. All right, so I think I'm actually going to be reusing this. Let me see which resistance. It doesn't specify that it's an addressable one per se. It's just an RGB LED that has the 3 legs for each primary color, and then the 4th one being ground. And looking at this, we need red, red, black, black. So that is going to be the 220 ohm resistance. So I need a total of 3 of those, 1 for each color leg. Take a look in the kit here because I know I have a couple of those open already. So I've got one out already. Let me see here. Oh, I got a couple different ones here. And we got that one, and then there's the second one, and then I need. Nope, that one's not the right. Nope, those are 1000 ohm. Looking at the colored bands on them, just as a bit of a refresher. And here's the third one. All right, thought I used at least 3 of these already, so instead of breaking them off from the other item. So yeah, so we read these from left to right with the tolerance band being on the end. A pack of RGB modules by accident. Oh, okay. At some point, I would love to be able to play with some of those, but I mean, this I'm already excited to at least be doing this because this I haven't worked with these before. I'm very much looking forward to it. It looks fairly self-explanatory, but yeah. So the so she doesn't indulge too deep into the fact of the LEDs still requiring the resistor. It prevents the LED from pulling too much power. Now, in the past, we had used individual LEDs, right? So this one I'm holding is a yellow one, right? And the yellow one has one positive and one negative side. And this will only produce yellow, which is also the color of the plastic, right? That requires the resistor on the positive side to prevent it from pulling too much power and burning itself out, right? That's still true into today's exercise, but we're just going to be hooking up a resistor to each positive leg of this guy. So this is going to be our LED that produces multiple colors, as we had said in the example. Now, a little difficult to see here. I realize this thing sucker's blurry, but one of the legs is longer than all the others. That one's our ground. Yeah, ultimate power. I'll take it. Right, now, there are indeed a total of 3 different colors in this one package. That's why it's got all the little legs. So what we're going to do, I'm going to look at our diagram here, and knowing that the longer lead is the ground, that means that since the ground is the second wire in our example, I should be sticking it into the board this way, not rotating it the other way around. So we're going to go into this way, and it looks like we're using, doesn't really specify which numbers, but that's okay. I'm going to spread them out here and get them plugged into lay breadboard, like so. So now each of these are in their own respective numbered hole here. So I've got holes 27 through 24 occupied, with the ground being the second one. Come on, Pyro, you know the rule. You're not late. There's no late to this. It's a stream. We're doing streamy things. Glad to see you, though. Hope your day was well. I know I had a fairly crazy kind of day, but it's okay. What do we got here? All right, pins 9, 10, 11. Okay, so I need a total of 3. Count them 3. What do we have here? I've got, how many colors do I have in this one? I've got 1, 2, 3, 4, 5. I thought I had one of these that was 3. Yeah, here we go. Here's one that's 3. Just to keep things a little, consistent and compact. Oh, good. I'm glad you're feeling better. It's no fun being sick. Our example is orange, green, and blue, but that doesn't matter. Those are just the different colors that we have in the example. So I've got 3 wires, and I'm going to plug them in on the 3 multicolored legs with a resistor between the 2. So as a reminder, the break that's in the center of the board here is electrically broken, so the contacts on this side are separate than the contacts on this side. So then we'll be able to hook up the resistor between the 2, right? So let me get these popped into the board here, and then we'll get ourselves wired up and then get some code going and make some colors. Very much looking forward to this. Now, I just have to be careful as I stick these in here to not short them out. It wouldn't really do any harm if these were to touch between sides. It would just provide an additional path for the resistance to go somewhere, but I don't want to do that in an effort to not mess up the project. Okay, so I got those 2 in, and I got 1 more. Gotta go in on pin number 24. And then make sure, excuse me, I can't show this to you guys and look at it at the same time. My eyes are good, but they're not that good. Alright, so I've purposely skipped over the second pin in our alignment here, being that one's the grounding pin. Right, so I have my ground still hooked up to the grounding pin on here, right? So I'm just going to skip over that one, and I'm going to hook up our colors into our friend here on the resistor side. So in my case, we're going to go blue on 27. Skip 26 because that is the grounding pin. And then 25 and 24 are my other 2. So I've purposely skipped the one where the grounding leg is. Now there's no connection between here and here. I'm just going to be plugging in the grounding pin in here, which to make life a little easier here, I'm actually going to do that. And then 26 is right here, like so. So I've got the ground here going to pin number 2 in my layout, and then the other 2 colors on the end, and then that is at least the breadboard side. So now I just have to plug in my other end into the little buddy here, our little hero board. Before I lose it, actually, I'm gonna stop quick and put my photoresistor away so I don't accidentally misplace it. Did you fix your metal grinder earlier? Had a couple of burnt out wires, soldered them back where they should be and fixed it. Oh, nice. Yeah, well, that's the one thing about motors, is that they're really good at burning stuff out. Because when motors hit resistance, like of you cutting something, or in this case, you're grinding against something, that will cause the appliance to draw more amperage. And if it pulls more amperage than what the wire is rated for, they melt or they burn. So the idea is that you would hope the cord is thick enough to cause the breaker to trip before it would melt. That's why when it comes to the wiring in your house, the breakers are rated lower than the combustion point of the wire in the walls. So that if you accidentally plug in too many things into one circuit, the breaker trips. So that you are sitting in the dark, but your wires aren't on fire and your house is still standing. Comes in handy. Because nobody wants cooked wires. You don't want them here? You don't want them in your walls. No one wants them in their walls. My goodness. Yeah, we're playing here. We got 9, 10, 11, and ground. So ground is right here. And then it was in this order. Battery powered grinder. Okay, that makes sense. Yeah. Yeah, let's see if I got this right. I've got bad eyesight. Let's see, that's 8, that's 9, 10, and 11. 9, 10, 11. Glorious. Ground is in ground. I put ground in 26. And then those aren't touching. Okay, beauteous. So, for the breadboard side of this little sandwich we're building here, I've got everything hooked up. We've got our resistors on the power legs. We've got our ground going back to ground. And the power is being delivered on the right side of our resistor, flowing through here and then returning back on the common. So that's how we can actually have 3 different inputs of 5 volts of electricity, but 1 return path, because it's all common to the LED, which is kind of weird to think of it like that. It's a bit of an interesting little appliance. So yeah, okay, so one thing I did not do is I did not clear the previous code from the board before plugging this together, so shouldn't do any harm though. We might get some weird blinkage from the previous code, but it should be easy enough to reset once we get the code up and ready to go. So physically speaking, we got this part sorted, so let us switch back to the laptop and start putting our code together. All right, let me see here. All right, beauteous. Okay, so now that we've got our wiring physically hooked up, let's get a terminal rolling here. And we'll start jumping back and forth to bring the code across. Who changed my background? Microsoft. What are you doing? I had the default background. I mean, it's a nice picture, but it's not mine. As a matter of fact, it's not my... Hey, that's not my artwork. I really should not have that on stream. Let me change that. Oh, hold on. Microsoft got iffy on me here. I don't think anybody would lose their mind over this, but you know what? I'd rather it be the default. Alright, beauteous. You didn't see anything! Alright, so we're gonna make a new file. And we're going to save this as day 8. Alright, beauteous. We have that. I just realized you guys couldn't hear the music because I'm silly. We can hear music now? We better be able to hear music now. I see the bars moving. That's what I get. What I get for muting it temporarily. I forgot I unmuted. Alright, so we got that. We actually can hear stuff now, which makes me happy. Okay, alright, let us dig into the code. on our fun little adventure here. Okay, so with any project with the hero board, we need to tell the compiler that we're using the hero's hardware. That's what the include is for. I've mentioned this multiple times. I'm going to continue to mention it until we're finished with all the 30 Days of Space project, because if we don't include this, everything we have below it isn't gonna work. It's incredibly important that we don't exclude this. This goes above all of our other code here, which I find really funny that it's not listed in this little default void setup and void loop. Ain't gonna work without it. So we're gonna move that down, slap that up there, have a good time, and I'm gonna save it. Okay, so now we have our include, which means everything else we have in here will actually function on our behalf. Isn't that fancy? All right, let me see where we're at here. Okay, so each color in an RGB LED is controlled with a different pin on the hero board. Only pins 3, 5, 6, 9, 10, and 11 on the hero board support the PWM function, which is indicated on the board by preceding those pin numbers on the hero board with the tilde character. Interesting, I didn't notice that. Check that out. Okay, let me zoom in on that. Hang on, let me bring that a little closer so you guys can... It's... Hang on. It's not doing what I thought it was going to do. Copy image. Paint. Let's try that again. Okay. All right, so yeah, it's obviously, this would be infinitely better than me trying to show you on the board because this camera's not crisp enough to show this. That little tilde, I didn't actually pick up on that little detail, and I did notice that when I was holding it, is on 9, 10, 11, then pins 3, 5, 6, and 9. Something to note, you'll notice here that these two are indicated with green, but there's no wires in there. That is just to remind you that any ground, so the ground over here or the two pins over here, all the grounds are common, so they're all electrically speaking connected, so it's valid for me to have plugged in that ground wire over on this side of the board. Just a friendly reminder on that part. Yeah, okay, so that's what the... Oh, I'm silly. Look at this. It's literally printed right here. Digital PWM equals the tilde symbol. It's literally printed right here on the board. Helpful. Okay. All right, so it says it right there. Only those pins support PWM in the analog write function. Now, knowing that there are pins that don't support it, I am purposely later in the exercise going to try to use this function on one of those non-programmed pins. I'm curious what kind of error it's going to throw, because I would think it's probably going to throw something fairly cryptic. I doubt it would very nicely tell you that you're doing it wrong, but I want to see what wrong actually looks like, because up until this point, it didn't matter which digital pins we used, as long as we just chose one that was digital for the digital stuff and analog for the analog stuff. In this case, this specifically requires us to choose one of the tilde holes on the board. So that's fine, but I am curious to see what's going to happen. Now, we've worked with constants before. These exist before the first void setup, which declares our pins. So that is going to go directly below our include. And thankfully, we looked close enough at the example here, and they lovingly gave us the names of which colors was where. So pin 9 was the blue one, which means 9, 10, and 11. If I look at the example, 9, 10, and 11. So 9 was, what did it say, green? 9 was blue. So blue, green, red. So blue, green, and red. Interesting. So red is the one. Now, if I was smart about this, I would have used colored wires that match the color of the LED, what color it produces. But yeah, that's smart. Smart's for another time, apparently. Naturally, I could have wired this up anyway, but that's just the way our example is written. See, now this is one of those things where having the code being meaningful, variables. This is one of those times that having the variable being a meaningful variable comes in handy. I know which of the pins is the red one as long as I plugged it into the board the correct way. So that I know which one's red, green, and or blue. When you're writing code, that not only that you have to use, but also revisit later. If you grabbed out this project, like I am revisiting, this series, like 2 weeks later, this is the kind of self-documentation that's super important. Having your code tell you what it's for. There's no mystery on what these pins are for, knowing that when you see that they're hooked up to an LED. So let's see here, what else we have here. Define a set of constants to represent 4 different brightness levels from our RGB LED using the PWM pins and the analog write function. PWM can be set values ranging from 0 to 255, as we saw in the example video, which we will demonstrate by adding 64, roughly a fourth of the range, to each preceding value. This also demonstrates that our constants can be computed using an expression that includes any previously defined constant. However, the expression cannot include variables or values that could change during execution. Okay, so that means you can reuse existing numbers, but that just means that since they're constants, right? So a constant means the value can't change, right? So this means that the way we declared this, if we want it off, it's a value of a 0. If we want it dim, it's at 64 out of 255. Brighter adds an extra 64. Brighter so, another 64, and then the brightest being 255, which is max brightness on the scale, right? So that is going to vary the voltage. So full brightness is going to be 5 volts out each of the rails. And then all those different brightness levels are varying the voltage different degrees to get us the different colors. I find it interesting though. So, but it's just simply saying that since these are hard coded, that they can't change mid-code execution. That doesn't mean you can't write the code to be more variable, but honestly, you kind of don't need it. You absolutely could use that concept if you'd like, but it's perfectly fine as it is. So let's see what the name of our variables are here. We've got off, which is pretty self-explanatory. Dim, we've got brighter, which takes the value of dim, adds 64, and that gets you that. Bright is taking brighter and adding an additional 64, brightest being the max value. So as you can see here, if we changed dim to be a different number, to not be equal to 64, say it was, 80, right? Then we would be adding 80 and 64 together because we are calling on the variable's name. So even though it can't change mid-execution, if I wanted to shift this by an extra 10-15%, I could just adjust these base numbers to actually change our outcome on what the different levels of brightness are. Think of it kind of like a dimmer switch that has the buttons with the predefined brightness. That's what this is. That's literally what this is doing. It's giving us 4 different brightness levels and off. All right, we got that out of the way. What else are we doing here? We can change this constant here in one place to change how long each color is displayed. So we have a constant of the delay for each color. Now, as we had seen previously with this stuff, a delay of less than 50 milliseconds isn't really noticeable. So we can make the delay longer to have the colors show for a longer period of time, but we generally don't want to go lower than 800 milliseconds, or excuse me, 500 milliseconds, or we might not quite see the color we want. Okay. Now, finally, it's time to throw some stuff into void setup. Let's see what we're working with here. So it says set each of our PWM pins as outputs, which makes sense because what we're doing is we're going to be sending voltage out on this. And since setup only runs once, that's why we're putting our pin mode in here. Obviously, we only need to set what the pins are doing once in this exercise. If for some reason things were to change, that would involve rewiring. So your pin mode almost always is going to end up in the void setup. I don't picture it going into the void loop at any point. I'll be interested to see if any of their exercises prove me wrong in that regard. But so far, I don't see any reason why you wouldn't have these in void setup. You only need to define what you're doing with them once, which is easy enough. Okay, now we've got a fair amount of stuff going on here, but nothing that's really difficult, right? So let's delve into this to see what we're doing. All right, so we go into the loop, and it says first demonstrate our different PWM levels by slowly brightening our red LED. So we could see here that our display color is off, right? So it's off, off, off. Now, if I click on this, I'm looking. Display color, did we? I don't think we declared that anywhere. How does it know that's a PWM function? Let me scroll back up here. Oh, I didn't scroll down far enough. Okay. All right, so let's read before we start moving that code around. Display color is a function that accepts 3 parameters representing the desired intensity for each of the LEDs in the RGB LED package, essentially. Each parameter pass must have a type. Here we match what analog write will use and a name to be used inside the function to refer to the parameter. The parameter can all be included on a single line like void display color and then byte red intensity, green or blue. However, if we display each parameter on its own line, we can add a comment to each for additional clarity on what it's for. So, if we look at this, we can see that we have a void function called display color. So I got a little confused there. I'm like, where's the function? I see it. I don't see it declared anywhere. The declarations for this kind of stuff can go in a couple different places. I'm used to having the declares of the functions further up in the code and then you call them. It's valid for it to be in here this way. It's just not the way I'm used to reading it. But then again, I'm used to working in other languages. So I don't know if it's technically legal to compile it the other way. I don't know. I'm going to play with that to see if that matters to the compiler. Because some languages, if you if you try to call a function before you've written it in the code, like the block of code that says what the function does, if you're calling it before you've declared it further up, usually it throws an error saying, I don't know what this function is. I don't see it anywhere. But it looks like in the compiler for the Arduino, it doesn't have to be above, which I'm not gonna lie, is to me a little confusing, but okay. Now, as we can see here, the void loop is there, ends there, and then the void display color function is outside of the loop, which makes sense because it's its own function that we can call on. We wouldn't technically want it in the loop. We're going to call it from within the loop. Technically, though, I should actually be able to move the display color function code and put it above the void loop, as long as it's not above the pin declaration. So I probably should be able to do that. Regardless, I'm going to do it the way they want me to do it, and then I'm going to play with it, because I'm not the biggest fan of that. I kind of like to be able to see the functions I'm calling, but I am not stalling. I'm just bothered. But that's okay. So let me get this stuff. This is just simply preference, and as long as it compiles, you could do it either way. But I'm gonna be honest, I don't like that. Just because to me, it feels a little more confusing. Audio set. The hedgie is real. Alright, and then we've got our void color function underneath the main loop, which for now, that's where I'm gonna be a good bean. I'm gonna stick it underneath it. And then I'm gonna see if it lets me put it above it, because I kind of don't like it down there. You shut down randomly? That's not good. You went from minding your own business to like looking like you're like this, like oh no, that's not good. I'm glad to see you're back. Welcome back. Okay, so before I I'm glad you like it. I like it. I find it silly. All right, before I can send this, I didn't plug in the board. So let me plug in the board into the computer, and then we will start sending some code. Now, I did purposely switch to this because I still have the previous code from the last exercise on here, and I'm kind of curious to see. I don't think we ever used any of the same pins, so I don't anticipate anything happening over here. We'll see here in a minute when I plug it in. Okay, all right, so as I expected, nothing has happened on our multicolored LED. Now, something you are going to notice over here is that the example LEDs on this that were supposed to read the values from the charging circuit as we were following is getting no reading. So technically, our solar panel is unplugged, and that LED is going to blink forever because there's nothing to increment it. It will never stop and indicate fully charged, which would have been it going solid in color. I digress. I'm going to clear that code, push our new code, and then we're going to see some action here. Alright. Boop. Alright, so first things first, we're going to, before I do anything, verify the code to make sure I didn't miss any parens or anything else. Okay. So, good on me. I didn't miss any brackets or braces. So I'm going to go into the tools now, and we're going to connect. Looks like we're connected already. Yes, I believe we are. Okay, so let me upload the code, and we'll see what happens here. Upload. Beep boop. All right, we are uploaded. So, as a reminder, once it's uploaded, it then clears the previous code. So that's why our LEDs over here stop blinking. Now we could see here, our little example friend here. Hang on, let me hit the light so it's a little bit more visible. Okay, so now, howdy mountain man, welcome on in. We're playing with our multicolored LED this evening. It's the first time I've ever programmed one, which I find kind of cool. So as it said in the example, the first thing that this function does is it cycles through all of our available colors at the initial brightness. And then from there, it then cycles through multiple colors together and then eventually ending with it being off. Now, this particular example doesn't have anything to actually stop this from cycling because it's a loop, right? It's just going to loop through the example, right? But say that we wanted the LED to be a specific color for longer, right? Yeah, so let me get us back over to here. Let me full screen this now because we're going to toy with this a bit. Okay, so I'm very grateful for the comments here to remind us all that the byte is anywhere between 0 and 255 values, which is perfect for this example. It allows us to initialize the entire space just fine for what that can hold. All right, and then we can see here that the analog right function then takes our intensity for the red, the green, and the blue, and then it sends it out on the pin. Now, before I do anything else with this, I'm gonna move this block of code for the actual function for displaying. I'm going to move it. I'm gonna move it above the void loop and see if it gets upset with me. I'm gonna save that. I'm gonna verify it and see if it loses its mind. I'm gonna push it. Technically, nothing should change. Nothing has changed. Okay, so looking at the bench camera, we can see that the LED is doing exactly what it was doing before, but I just moved where the function lived in the code. So, first order of business out of the way. I can have the function further up and the compiler doesn't get upset with me, so there's no error generated by that. Certain languages require your functions to exist above where you would call for to use them, right? Because the code that runs every single time is the loop, right? It runs constantly until it loses power, right? The setup function runs once, which we have up here, and then our void function display color I actually have above the loop, but when it goes to run it, well, it just calls it from up here. Doesn't matter that written in the code it's up above in this compiler and programming language. Hi, Dratron. Welcome on in. Haven't seen you in a little while. Hope you're well. So that's good. That actually makes me feel better because I prefer the function to be up above. Doing good. So these are all predefined values that we have here, by just choosing the phrasing of off, dim, brighter, bright, or brightest, right? And we can see here in our loop that we have a mixture of calling the function that then sets the brightness of the LEDs, right? Or I say LEDs, it's LED, but each individual color within the LED, right? So we can see here display color of just all off is just nothing. That's why it starts with nothing being visible when I click to the go button, right? And then you can see where this color delay comes in here, right? Now that is a variable, and you can see we called it a whole bunch of times, right, for the delay. Because why would we want to tap the type, the number for the delay, over and over and over and over again, unless we want the variable to be different for one part of the code, right? And if we didn't want to change what was in the variable, which we totally could, we could hard code, but normally you don't hard code things. In this case, we just have our color delay living up here, and that means between each color change, there is 500 milliseconds of time. I can increase that value and make the LED cycle through the colors slower, right? By making this number bigger. Right, and if I do that, slap on an extra 0, and then I tell it to go, verify and send. I told it 5,000 milliseconds. So this is going to cycle a lot slower now, with the first value being off. And that is our introduction into going much slower. We can see here that we are cycling through the colors, but we're taking way more time in between them now. And then there's off, right? So we have that available to us. I'm gonna switch that back because that's a little too long in between color shifts. Now we can see here from left to right when we look at the function. It's red, green, blue. That's the order that they're declared in, which means that when we look at this, it's red, green, blue in that order. If we switched around the order they were declared in, then they would display here in the other order. So we just have to keep in mind this is the order that they're done up in. Because these are the physical tie-outs to up here, the physical pins, 9, 10, 11, 9, 10, and 11. But if I were to put in the void function these items, or change the order these are loaded in, right, if I put blue above red, well, still down here, it's going to, it doesn't matter that this will change the way it's put out there, but it would be in the other order. Just, I don't want to make this too confusing, but basically just, you read from top to bottom as red, green, blue, which just simply means red, green, blue, looking at it this way. Just because it shifts a little bit when you're looking at the code. I can prove that. because if I'm right and the first pin is red, then I could go and I can comment out all the code that's there. Right, so I've just commented out all the example code, and if I were to grab one of these, and then I go and just go with these one at a time. Now, if I don't put the delay in between, it'll cycle too fast. It'll be hard to see. So I'm just going max brightness on the 3 colors, right? And the order I'm calling this is red, green, blue. So it should be red, green, and then blue. I'm gonna send that code, and then we should see it cycle in that order, if I've got this right. Or I'm wrong. I like being wrong. It makes things interesting. What did I do wrong? And that's bright. Made a mistake. What did I do here? Display color. Right, value 255 passes as red intensity. Oh yeah, the hover even tells you that. The color delay. Zero for red. Max green, which is what I have. And then max blue. How did I mess that up? Right, a 4th. That's where we cycled through those. Display yellow by mixing red and green, green and blue, and then red and blue for magenta, which we did see. And then bright on everything should... Alright, I'm game. Let's see if I actually try to go for white here and see what I get. Because I'm not gonna lie, I'm a little curious as to what I goofed up here. I'm gonna manually put in a delay here of 1,000. Oh wait, I don't want that there. I want that delay underneath because I want to display white for 1,000 milliseconds. But I don't want to modify all of them. So we're gonna go brightest on all 3 colors. So I'm gonna save that. I'm gonna compile it. I got it compiled. I'm gonna push the sketch, and then we should get red, green, blue, and then white, because I have all these set to. Oh, comments are important, folks. White, just so we know what it's supposed to be. All right, upload. Beep boop. 1, 2, 3. I'm a little confused here. I've got, it was supposed to be red, and it looks like the initial color is green. So I've got green, red. It was supposed to be blue. Unless I misunderstood the primary colors on this. Okay, I did hook this up right. Double check the wiring schema. Now granted, it is getting... That is supposed to be white, and if I look at our individual LEDs here a little closer in my camera, as you folks are getting blinded here. Let me drop the intensity so I can look at that head on to see if the individual markers are lighting up. Maximum brightness is not a smart idea, otherwise I need sunglasses. What could potentially be what's going on here is maybe max brightness is not such a good idea. So let me drop our intensity here and see what that gets us. One, two, three. I'm getting 3 colors, and what do I have in the code? I've got a mistake in here somewhere, because I'm telling it to make 4 different colors, and I'm getting 3. So why am I missing one? Should not be missing one. I'm going straight to green, and then red, instead of blue. As the blue intensity. Okay, so let's see here. I've got red pin, green pin, blue pin. Red, green, blue, as I have it up here. Alright, out of my own curiosity, I'm going to put this void function back down where I had it and see if that's the cause of my problem. Now, this is initially where it was. Well, let's see if that makes a difference. Huh, no, it does not make a difference. Okay, so the location of that void function display color doesn't matter in that regard. Red pin. Red pin is number 11. Green pin is supposed to be number 10. Alright, let me turn the lights on here. Let me make sure I didn't accidentally misplace one of these jumper wires. I've got serial, AREF, ground, 13, 12, 11, 10, and 9. 9, 10, 11, if I count from the bottom, that's 8. I am plugged into those 3 appropriate pins. I'm looking at this from the top down. it's actually working correctly. Okay. Now, so looking at the LED head on, which I'm not gonna lie, it hurts a little bit. All three of those are actually turning on in sequence. It just really, to my eye does not agree with the color it's putting out, but it's doing it. It's doing it correctly. Well, let me rephrase. I'm not getting the colors in the order I think I'm supposed to be getting them in, but all of the individual LEDs are turning on inside of the LED package. So I am getting 1, 2, 3. No, I am only getting 3. That still doesn't make sense. And this is going to say I have at least everything I'm requesting. It just doesn't match color, but that's not right. What the heck am I missing here? I've got... I'm calling on dim for that first intensity. All right, here's what I'm going to do, and I'm going to show you. We are going to go through each of these one at a time and then upload the code for each shift in color. I'm not interested in it cycling because we're trying to figure out why it's not working the way I'm anticipating it. So to do that, all we're going to do is comment out these. So that should be the only thing we're going to get here. There's no delays because it's just going to loop over the same color, right? So this should be the red at 4th intensity. So I'm going to send that and we're going to see what color we get. Nothing. I've got nothing. Okay. So let me go to do the green and see if I get green. Okay. I got green. Cool. I'm going to comment out green and then go to blue. Okay. Well, there's some of my cause for confusion. Well, that's fascinating. I think I have a damaged LED I'm working with. I'm missing. That's supposed to be blue. I'm not getting blue right now. Let me scroll back up to the pinout on this and just be absolutely sure I hooked this up correctly. I might actually have, I think I only have one of those in this kit too, which is disappointing. I do, I only have one of these in the kit. So, we're going back to the drawing board. I'm going to disconnect this and I'm going to double check where I plugged everything in. So, before me, I have our diagram, which we have here. I'm going to have for you guys while I look at this. So it's supposed to be, let's make sure nothing's touching. That definitely cause grief if I've got a short here. None of those are touching, none of those are touching. The ground is on pin 26. Red is the first in the alignment here. I'm gonna grab any of the wrong resistors. I'm supposed to have 2 red, 2 black. So I'm supposed to have. Do I actually have that? I've got 2 red, 2 black, 2 red, 2 black, 2 red, 2 black. Okay, so I've got the right resistors, 220 ohms, which is correct. I've got pin 26 hooked up as it's supposed to be. 27, I've got that 25 and 24. Let's put it there. I skipped 26. So I've got 24. Nothing, 23 and 25. Okay, so looking at this, that looks correct on the actual breadboard side. I didn't mess up any of that, so I do have an electrical connection between there. Blue, the first of our alignment, is supposed to go into number 11. Did I actually do that? I didn't do that! I hooked up the wires backwards! Alright, hang on a minute. That would explain why colors don't work. Alright, so far left is supposed to go into pin number 11. I didn't do that. Let's do that. Okay, and then next in line is supposed to be, in this case it's the purple wire for me. Purple wire. It's supposed to be next to it. And then this one after it. Like so. Okay, so what I just moved was the hang on. I am gesturing to something you cannot see. Boop, there we go. That's better. Okay. This side I had correct. I messed up this side. I purposely used some that were pre-stuck together to try to make this part a little easier, when in reality it was my downfall. Hey Pine Sap, welcome on in. I am troubleshooting because I'm silly. It was not damaged. I hooked it up wrong. So now we should get the colors that we want in the correct order. So let me apply some power here. And I don't remember what color I left off on. Oddly enough, the board should have remembered it because the code technically would have been the same regardless. But I've got nothing. That's okay. Let me send some stuff to it and we'll see what we get here. Alright, I am going to... That's supposed to be blue right now. Interesting, I don't get blue. Let me see if I tell it that I want red now. If I actually get red. Ah! Okay. Alright, so we get red. Red looks like red. That's exciting. Helps when you have it wired correctly. This is why it's unbelievably important, folks, to double check your wiring. Because I still think I might have a damaged LED. But I'm a little less stupid in that regard. So I did get green right. So if I comment out red and then uncomment green and send that, got green. Not too shabby. Now, the last one in the gobbledygook here is supposed to be blue. And I'm going to send blue. And we've still got nothing. So, blue, if we take a look at our friend here, blue, according to the example, is supposed to be pin 9, which is the first in the lineup. And it's supposed to be the bottom corner. So let me double check that yet again to make sure that's fully seated. If not, I might try using a different jumper wire and see if that helps. Because we are not currently getting anything on blue. Now, I know that I have it in the right hole in this regard because there is supposed to be one available before the next block starts. So this is plugged in where it's supposed to be, and it's supposed to be far right on the board here. And if I take a look here, I see what I did. I see what I did. I skipped a hole. I skipped a hole in the breadboard. It's really hard to see. If I'm gonna move it a little closer here, you will see that the control pin is not plugged into the same row as the resistor, which is why it doesn't light up. So for me to fix that, all I'm gonna do is I'm just gonna move this over to pin 23. And surprise, surprise, I've got blue now. So now when I tell it I want the color white, that's gonna look more white. Because now it's going to initialize all of the colors. And lo and behold, I've now got all the colors functional. They are all on at the same time in the, let me turn off that overhead light, in the dim intensity. I don't have it on high, I have it on dim. Something was loose there. Whoop. Something's not perfectly tight because I'm jiggling the board here and it's causing it to cut in and out. But now this is good. See, the best way to test, at least to make sure that our friend here can successfully cycle through the other colors, is to set all of them in the on position. That confirms to me that all of the LEDs that are inside of the package here are not only on. Oh, can you see that on my hand? Kind of. There we go. Let me turn off my lamps. This is actually a decent little exercise to give you a better idea here of what we're dealing with here. Just a moment. Okay, we are not perfectly in the dark, but it's close enough. If I hold this upside down, right? Check that out. You can see all of the different colors that this produces. I can't turn off the external monitor. I forgot about that. That's okay though. You can still see it. All 4 individual colors. If it doesn't cut out on me here, because I know the wires are a teensy bit loose. Come on now. There we go. You can see all of them on my hand. And that is because it is truly 3 different colors of light that are in the one package. So that shows very cleanly, I know it's blinking in and out of here, that all of the colors are not only available, but they work. These boards aren't exactly designed to be flipped upside down here when you're breadboarding here. There we go. And if I double check that, okay, I now have all of that going on here. Echo, turn on Team Rocket. Okay, so now I'm gonna leave the other light off. I'm gonna reinstate the original code that we got from the example. And we are going to see something that should be a little bit more impressive. Yeah, that's what we're talking about. We are strobing. That is more like it. So we are now cycling through all the colors at a couple of different intensities, and it actually does cause a couple of them to be on at once. As it does say in the example here, is that Near the end of the cycle, it displays yellow by mixing the red and green LEDs at once. Cyan, which is more of like a light colored blue, by mixing green and blue. And then magenta, which is like an off pink, by mixing red and blue. The colors cyan and magenta should sound familiar if you do anything with printers, because those are the colors that are used in the pigments that are used to make colored prints using a printer, whether that be laser or a inkjet, or sometimes bubble jet. Those still kind of float around too. So that, I'm gonna be honest, caused me a little more trouble than I thought it was going to, but it truly didn't seem to be too difficult, because since this is code control, this indicates not only do I have full control over any color that that could produce, but further down, when it comes to producing the code that we can use here to make those colors mean something. Right now, that just proves that we actually have the ability to control the color of the light, choose whatever color we want, and then later down the line, those colors can mean something. Briefly in the example, she had mentioned that maybe like a serene blue, right? Or, you know, emergency red, right? Those colors, as you can clearly see right now, are just colors. They don't mean anything. But in your code that you write, and I'm sure code that we're going to produce here moving forward, assigning a meaning to the color is where that comes in handy. Now, obviously, if you had something that was over the top and super important, you wouldn't want colors that look incredibly similar to be next to each other of increased intensity. Like if there was water in the, you know, bottom of the ship, we're taking on water, well then we probably don't want blue to be right next to cyan, right, which is that light colored blue, which could just mean that the water temperature is a little warm, you know, something weird, right? So in the case of something that's analog like a light, values are a little difficult to distinguish with your eyes, but something that is obviously different, like the blue looks clearly different than the green, right? So if you're using something as a visual marker on something you're doing, then having colors that don't too closely overlap is the right way to go. Which is why early on in the early on days of computers and storing computer values, in the early days they used vacuum tubes, and the vacuum tubes would be set at different levels of brightness. Now the problem with this is that when it came time to read those values out of the vacuum tubes, the varying levels of brightness made it pretty hard to distinguish on what level of brightness that the value is stored at. So if 5 was supposed to be kind of like a dim and 10 is like a medium brightness, well, what I think is bright and what you think is bright aren't going to be the same thing. That's just how life is, right? Because we have different eyes, we see things differently, and there's also variability in the way a vacuum tube lights up. There's different levels of brightnesses that come from a vacuum tube. So if I took out the one that was installed, popped it out, popped in a fresh one, it's going to be a different brightness. And then the way you have to identify that number in the meaning that's assigned to it is going to be hard, right? So that's why in the space of computers, we distinguish things with 1 or 0, on or off. It is really easy to tell if something is turned on or if something is turned off, right? When it comes to storing information. That's why the golden standard is binary when it comes to storing information, because that's easy, you know? On's on, off's off. There's no distinguishing issue with that. But when it comes to something like this in colored lights, you just have to be careful that you don't end up assigning something that's too similar to another color. Other side note, when it comes to colors and assigning meaning to them, people are colorblind. There are 100% colorblind folks that have floated around out here in this world. So if you are thinking about assigning color to your project, there's no issue with that. But do keep in mind that if that value is supposed to be something that's important or someone has to be able to distinguish what that means, go with multiple LEDs and have them in a row so that if the LED comes on, well then there's the meaning associated with it. A multicolored LED doesn't really do anybody any good if they're colorblind or partially colorblind. they won't be able to distinguish the colors, or they just won't be able to see it the way you see it. Like, blue looks different to me than it does to somebody else who can't see colors the same way. Which is funny, because if any of you have played, what's that sci-fi game? Among Us. They had the colored wired game where you'd have to match the colored wires as one of the activities. Well, the developers actually added symbols on the wires so that you can match the symbols or the colors, which added the capability of allowing folks with color blindness to be able to play the game and enjoy it just like anybody else. It adds a little bit of accessibility to the game, and same kind of thoughts apply here to something like this. Always be thinking about stuff like that. Because the way you interact and perceive the world is not going to be the same as everybody else. That's perfectly fine. Just have to keep that in mind. Also, that's why feedback's important, because if you forgot of something that's fairly important like that, someone can tell you, and then you can make the change and adjust accordingly. So yeah, that is day 8 of 30 Days Lost in Space. I'll have to admit, I did not think that LED was going to give me as much trouble as it did. But it did, but that's okay, because that is why we take our time, and I didn't give up on it. Now, don't get me wrong, if I couldn't figure out that I didn't have those pins in the right place, maybe we would have ended and tried to pick this up on another day, but that was something I felt was either the LED was bad or I didn't have something wired right, and that is honestly just how things go. You might not catch it in the first run, and that's okay. That's just the name of the game, but that's okay. What time is it here? We are looking okay. Okay, so give me a moment. I'll grab my device here, and if you could stick around with me for a few moments, I am going to pick someone for us to go say hello to. I'm gonna pop this out of here. Let me see who is currently rocking and rolling here in the online space. Alright, let me see if I could spell her name. Being able to spell, folks, is incredibly important, especially when you're trying to read into someone.
Everyone in my
Yep, nope, yeah, here. Got that. Is it gonna listen to me? It is. All right, cool. So we're gonna scoop that up. Fantastic. Okay, so Purple Chaotic Dragon is currently doing art in fantastic art-like fashion. So we're gonna go say hello to her. She's a fantastic being. She also does commissions if you want fun art or if you want a retexture. A little bit of a plug because she's awesome. By all means, she has a Discord. Ask her up. She loves to work with all sorts of fun models. Special place in her heart is the Hopkin. So, you know, if you want a Hopkin retexture, 100%, that's the place to go. All right, folks, I will see you next time. Enjoy the rest of your evening/morning. Bye-bye.
Tuckhead! Aw, you lovely bean.